Okay, here we go. So the first one, by far the easiest way to do this is to tangent is sine over cosine. So tangent squared is sine squared over cosine squared. And then you immediately see that cosine squared and cosine squared is 1. And all we simply have is the integral of sine squared. And so now we've got to do sine squared, this is maybe the most important one. It's the one we're going to see the most throughout the semester. So we got to know by hand, how to do the integral of sine squared. Okay? And how do we do that? So you had several of these. I think this was one of the examples in the book, and then you had several of those in the homework. And this is the half angle formula. So when you do the half angle formula, you get 1/2, 1 minus cosine 2x. Okay? That's how you do sine squared. Use the half angle formula. We're going to see it all semester. Okay? So any sine squared or cosine squared, you're going to use half angle, and you have this, and now this is one we can do. So you actually break it into 2 terms. So it's 1/2 minus 1/2 cosine 2x. And now we're ready to go. So now we've got an antiderivative that we can do. Do you have something to grade with? Besides what you took the quiz in?
Yeah.
Okay. So I see lots of pencils and black pens on the desk, put them in your bag. Just because I don't want to have to sit here and keep looking. So if you have your pencil or the thing, whatever you took the quiz in, put it in your bag. Put it down below your desk. So like that with your pencil right there. And like your pencil right there, put it in your bag. You got your pencil or your black pen, put it down in your backpack. Everyone, you got it?
I use pencil and
okay, so I have a red pen for you. I have an extra one. Here you go. Red pen. Okay? So here we go. So what is the antiderivative of 1/2? 1/2 x. And now we got to do antiderivative of cosine 2x. Which is a very easy. What is the antiderivative of cosine 2x?
1/4 sine of 2x.
So you're going to have sine of 2x. Because the antiderivative of cosine is sine. But then we have I'm doing the chain rule. We've got this 2 here, and then we got another 1/2 here. All right, so this 2 results in a 1/2, and we have the 1/2 already, so that makes 1/4. Plus c. Okay, so here's how you're going to grade it. Getting to this integral right here is worth 3. If you didn't get that, if you didn't get to there, it's basically 0 on this. Okay, so you got to get this first. All right, and then if you got that, then substituting in the half angle formula is worth 2. And then getting the right antiderivative here is worth 2.
Yes.
Okay, so I can't answer a lot of questions in grading, but
I was just going to say I used the property that tan squared plus secant squared equals 1.
okay, so did you get what, 1 minus cosine squared here?
I ended up getting the half angle rule through what?
Did you get 1 minus cosine squared here? Is that what you did?
Yeah.
Yeah. So if you did 1 minus, if you got to 1 minus cosine squared, that's full credit. Because then you do the half angle on cosine squared. So instead of sine squared, if you had 1 minus cosine squared, that's full credit.
When you reach the half angle, what is
It's fine. It's fine. Yeah. So I can. Yeah. So just use your judgment. I can't answer. I can't answer 15 questions on each of these. So just use your judgment. Okay. But if you didn't get sine squared or 1 minus cosine squared, then you don't get any points. Okay. Because that's the whole point. So score yourself on that one. Any questions on doing? So again, this is maybe the most important one for this part, is the how to integrate sine squared or cosine squared and use the half angle formula. Questions? So number 1. So what was that possible? 7? 7 points possible. Okay, ready for the next one? Okay, so right away we're going to do sine of 2x. That's one of our identities. It's the double angle, so it's going to be 2 sine x cosine x, but then there's another cosine x, dx. So sine of 2x is the same as 2 sine x cosine x. So that's the first step. And that's the same as 2 sine x cosine squared x. Is that, do you have something different to grade with? Is that what
Everything.
Okay. Are we good? And what do we do with this? You want to undo the chain rule? Yeah, because look, so you've got cosine squared, and what's in the inside here is your derivative over here. So this is a pretty easy undoing the chain rule. And so when we undo the chain rule, our first attempt would be cosine cubed x. We're going to have a 1/3, right? And then when we take the derivative of cosine, it's going to be positive sign. It's going to be negative sign. And then we also have the 2. So the 2 comes down. And then this is basically negative 1/3 cosine x cubed. So we undid the chain rule. So we apply that first identity, and then we undo the chain rule, plus c. Okay, so for grading, applying the identity and getting this right here, that's worth 3. Undoing the chain rule to get that correctly, 3. So this one's 6. Again, this exercise of grading it together is as much about learning it if you did it. Okay, so if you didn't do this, then I'm showing you how. Okay, I'm showing you how. Anybody have a question on number 2? Okay. Last one. How do we handle cosine cubed or sine cubed? Okay, if you remember from the example, and you also did it in your rubric, you start by writing it as cosine times cosine squared. And then here, rather than using the half angle formula, now instead you rewrite it using the Trig, Pythagorean. You rewrite this as 1 minus sine squared. And then, when you multiply it out, you've got 2 terms that we can do. You got cosine 5x times 1, which we can handle, and then minus sine squared 5x cosine 5x, which we can also handle. So cosine 5x, what's the antiderivative of that? Oops. That's 1/5 sine 5x. So real easy undoing the chain rule. Okay, what about sine squared? Boom, cosine, boom. Sine squared, then times cosine, and we got the same argument, 5x. Undoing the chain rule, right? It's the same as, again, we see it again. We've got the derivative cosine of sine. So we're going to do the antiderivative of sine squared, which is 1/3 sine cubed but we also need, if we were to take the derivative of that,
1/5.
we're going to need, so at the very end, we need to take the derivative of the very inside of 5x, and we're going to get a 5 so that we don't have, so we need a 1/5. And so that's, you could have 1/15, that's fine, 1/15. Okay, and so this, getting to this right here, plus 3. And then multiplying out, and that's plus 1. Distributing, so we're distributing the cosine 5x. And then finally, the last step is doing the antiderivative is another plus 3. So 7. So again, if you didn't get this step, you pretty much get 0 on the problem. If you didn't, this is the for cosine cubed or sine cubed. This is what you need to do. So split it into cosine and cosine squared. But now here you don't use the half angle. You use the Pythagorean identity to rewrite cosine squared. And then when you multiply it out, you're home free. You can do it. Questions on this one? Okay, so put your score out of 20. It went 7, 6, 7, right? 7, 6, 7 for the first one, 6 for the second, 7, so that's 20 points. So put your score out of 20 at the top. Any questions? And then flip it over, bend it up. Did you get the same answer? Yeah, fine.
6.
Anyone? Okay, so with these integration techniques, you're responsible. Our exam is Thursday. You're responsible for being able to do them by hand. Okay, and I've tried to emphasize that. So make sure that you treat the web work that way. And then if you're having difficulty, then you can email me a question, or you can come to office hours or set up an appointment. Okay, yes, sir.
Are we supposed to have all the trig identities memorized by Thursday?
Let's see. Some of these you definitely should know. But that's a good question. Let's see. All right. Yeah, so you have to know these because when we're in the midst of a longer problem throughout the semester, and you get, say, sine squared, you don't want to have to take 2 minutes to get your book out and try to find that formula. So you just want to have it at your fingertips. So, but I'll narrow it down a little bit here. So I'll just narrow it down to the very most important ones that you should have memorized. So I'll circle them, okay? Certainly, you need to know this. Tangent x is sine over cosine. Yeah, so the basic definitions, yep, cosecant 1 over sine, secant 1 over cosine. Cotangent is cosine over sine. This goes without saying. It's the most common identity. It shows up the most. For sure, you have to know that. Okay? And then these, because this is how you do the antiderivative of sine squared and cosine squared. So, at the bare minimum, yes, you should have those memorized. The rest I can give you. Okay? But if we're dealing so often with trig and all these different applications and problems throughout the semester, we should know the easiest formulas. We should just have them. We should know them. Is it fair? And anything else that's not on this list? Okay, good question. Any other questions? Okay, so I picked those 3 problems especially because like those are the most important ones that you need to know from that section. Sine squared and cosine squared. Or sorry, sine squared, which was the first one, or cosine squared. Sine cubed, which is the last one, or cosine cubed. And then using undoing the chain rule, right? Using undoing the chain rule with sine and cosine. So for instance, cosine to the 5th, sine x. Recognizing that that's undoing the chain rule and being able to do that. So that's why I picked those 3 for the quiz, because they're kind of the most important ones that we'll see the most often in the future. Okay, so let's go on to the next section, which is called partial fractions. So using partial fractions to simplify or solve antiderivatives. So the first thing, so we have integrals like this. So we have a quotient, and we see that. So we got to think about the techniques we've learned so far, and we got to see that none that we've learned so far would work for these. So this first one, 2x cubed over x plus 1. Undoing the chain rule, will it work? No. So it's not. We don't have that setup that we need for undoing the chain rule. Okay. Undoing the product rule. Well, maybe that first one. The second one, it's three things multiplied together. If we made it a big long product, we'd have three things. So that second one, no, that'd be kind of ugly. The first one, maybe we could give it a try. But what we want to recognize is this new technique of partial fractions. When you have this, like a quotient of these polynomials, which is called a rational function, right? So these are rational functions. And rational functions where undoing the chain rule doesn't work. And undoing the chain rule is our go-to. That's our first one that we want to go for. Okay? But so then these are rational functions where that doesn't work. So the first thing with this is to, if the degree of the numerator is greater than the degree of the denominator, then we want to long divide first. So by this is my shorthand for saying the degree of the numerator is greater than the degree of the denominator. Then we're going to long divide first. Okay, so how about this first one? Yeah, we would long divide first. Okay, so let's go ahead and do that. Let's just start this example here. And so remember how to do long division. So we got x plus 1. And we're going to have 2x cubed plus 0x squared plus 0x plus 0. Because we need all the different powers of x. But if it's just 2x cubed, then those are all going to be 0. 0x squared, 0x, and 0. Okay, so now x plus 1 goes into 2x cubed. How many times? So it's going to be 2x squared. Remember how to do long division of polynomials? So 2x squared times x is 2x cubed plus 2x squared. And then what do? We subtract. We're going to have minus 2x squared. Okay, now what? So we're asking how many times does x go into 2x squared? Minus 2x, right? Minus 2x. Oh, wait. We forgot to bring down the plus 0x. Remember long division? So minus 2x times x, minus 2x squared, minus 2x. Subtract and we get plus 2x, bring down the 0. And so x goes into 2x how many times? Plus 1, right? And we get, 2. So we get 2x plus 2, and when we subtract, we get minus 2. Okay, so what do we have? We have our quotient. We're going to say plus the remainder over the divisor is equal to that fraction. So this becomes 2x squared minus 2x plus 2 minus 2 over x plus 1. Sometimes when you long divide, then you're done. You're ready to take the antiderivative, which is the case here, right? This is one we can do. So we know we can do this antiderivative easily. 2x squared is going to be what? 2/3 x cubed minus x squared plus 2x. What's the antiderivative of minus 2 over x plus 1? What's the antiderivative of that right there?
2 natural log plus x
Yeah,
plus
natural log, because it's really x plus 1 to the negative 1, right? To the negative 1. And so we're talking about natural log. So it's going to be minus 2 natural log absolute value x plus 1 plus c. So this is an example where you really don't even use this partial fractions technique. You just, here in this example, when you want to divide, you have something that you can take the antiderivative of, and you're done. Okay. But sometimes this term, so these terms are fine, a polynomial, but this term right here, then becomes like a fraction whose denominator has the higher degree, right? So either something like this or something like this now is where we actually have to apply the partial fractions technique. If it's not easy like this, right? This is just natural log of x plus 1 times minus 2. But you get this fraction where now the denominator has a higher degree, and in some cases you have to use this partial fractions technique, which now we'll get to. So in the partial fractions technique, we're going to rewrite the quotient. So this quotient now, n is less than d. Okay, in what's called decomposed form. Okay, in decomposed form. And how do we do that? So we imagine that this was originally the sum of a bunch of fractions, and we found a common denominator and added them together to get this. So we're going backwards. We're splitting it apart into many fractions that we would have added or subtracted to get one fraction. Does that make sense? You know how, like, when you add and subtract fractions, you have to get a common denominator and you make one big fraction out of it. So the decomposition of a quotient is like pulling it apart into many fractions. So we got to think about what are the possible denominators we could have had to start with. So now we'll work on this example here. Example 2 to do now step 2. So what are the possible denominators we could have had that when we added the fractions together, we ended up with this? Okay, so as I'm erasing, you can think about that. Does my question make sense? So now we're doing this as a second example here. So we want to think about if we were to add fractions together here like this. What would the possible denominators be? What's one possible denominator that we would have had that when we added, we got 2x plus 1 and times x minus 1 as the denominator? 2x plus 1, right? And what else? X minus 1. Any more? Nope. Just 2. Okay, and so we want to account for a polynomial, the most general polynomial that's 1 degree less than that for the numerators. So what power do we have here? This is to the first power, right? So then if we take 1 degree less than that polynomial in there, it's to the 0th power, or just a constant. So we'd call it A. We say there's some constant. That's the numerator of this, because it's going to be power 1 less than the power in the denominator. All right, and then there's some other same thing here, power 1. So we're going to take 1 less, and let's say there's some constant b. So now we have. So if we added these two fractions together, we would get the original fraction that we started with. We just got to figure out what a and b are. Okay. So what we're going to do is we're going to now add these together. We're going to add these together and basically make it equivalent to the fraction we had, and then figure out what a and b are. So how do we add these together? The common denominator that we know is already, that's where we came from. And so what would we do to this one? We're going to multiply top and bottom by x minus 1, right, to get our common denominator. So then we're going to have ax minus a. It's going to come from this over here when we multiply top and bottom by x minus 1. Right? Makes sense? And then b, so this is b. What are we going to do here? Top and bottom by 2x plus 1. So it's going to be plus, and I'm going to multiply through 2bx plus b. So this is my a times x minus 1, and this is my b times 2x plus 1. So this right here has to be the same as that right there. So look, we've got an x of 5x, we've got 5x. What does 5x have to equal then? So our denominators are the same, so now we're just setting the numerators equal. 5x has to equal ax plus 2bx, right? So we're going to gather up the x terms, and that's going to be equal to the 5x. And then we're going to gather up the constants, and that's going to be equal to the sum of the constants. In this case, negative a plus b. All right, I'll stop. Did I lose anybody? Does this make sense? Okay, and so now we just, in this first one then, we're solving for a and b, so it's going to be 5 equals a plus 2b. So the coefficient, we're basically solving for the coefficient of x, which is 5, has to be the coefficient a plus 2b. And then you solve this however you know how, or whatever the fastest way is. The fastest way here is just to add them together, and the a's go away, right? So 6 equals 3b, so b equals 2, and then a has to be. So a is going to be 2, is it going to be 1? And so therefore, if a is 1 and b is 2, then this, the decomposed version is 1 over 2x plus 1 plus 2 over x minus 1. And so if we were to add those two fractions together, what would we get? Or what should we get? What we started with, right? 5x plus 1 over the common denominator. So we can just do it really quick. Do we get 5x? So we know we do x minus 1 top and bottom. So we get 1x plus 2 times 2x is 4x, 5x. And then we have the, over here we have a negative 1 and we have a positive 2. Positive 2 plus negative 1 is 1. There it is 1. So but now by decomposing it, we can take the antiderivative of this. That's step 3. Okay, so antiderivative of 1 over 2x plus 1. Absolute value. Is it right? Yeah, so, yeah, you're going to have, this is like undoing chain rule, right? Because you got the 2x plus 1 in there. If we took the derivative of it, we'd have a times 2, which we don't have there. We don't have a times 2, so we need the 1/2. Okay, this one? 2 times?
Natural log of
Natural
x minus
x minus 1. Do we need to clean up any mess here? No, because it's just x, right? So derivative of x is just 1, so there's no mess to clean up there. Plus c. Or, if there's limits of integration, there's a starting value of x and final value of x, do what you always did. Plug in the first one, plug in the second one, subtract, right? It's a change in a quantity. Change in the quantity, starting at the lower value of x, ending at the higher value of x, means final value of the quantity minus initial value of the quantity is the total change. This is
Am I a mistake? How did you get a half?
so if you're so it's undoing the chain rule. If I was to take the derivative of this, take the derivative of this right there, what do you get? Derivative is 1 over 2x plus 1, but I'm not done, right?
Times.
Times what? Times 2 by the chain rule. It's a 2 that I don't have here. So this is undoing the chain rule. I need that 1/2 to take care of that 2 that you would get when you do the chain rule. Does that make sense? Other questions? Yeah, please.
How did you get a equal to 1?
I just went back here to my formulas here and just figured out. So if I knew b was 2, then I can get what a is. Yeah, you just substitute back in here, and you can use either one. You can use either one of those. Other questions?
Could you go over again how you got from a over 2x plus 1 plus b over those 2 into the larger formula you used to figure out the 5a plus 2b?
This one?
Yeah, from the step
So-
just to the left of the right.
There to there?
Yes.
So I added these. I just added the fractions. So how do you add fractions? What do you do?
The
Common denominator, which was what we got, and then I just added, right? So I'm just, what do I need in order to make out my common denominator here? What do I need? I need x minus 1 over x minus 1. So that's then going to be, this is a time, I kind of did an extra step here. I multiplied it out also. So a times quantity x minus 1, which is x minus a. And then this is b times quantity 2x plus 1, because I'm adding the fractions. Other questions? Okay, so let's just jump to. So that's basically it. It's like you've got this fraction and you're pulling it apart into a bunch of fractions that would be added together to get that. Each of those are doable antiderivatives, whereas the original fraction wasn't. Okay, that's the idea of partial fractions. So another example. Try something a little different. Okay, this is a little more involved here. First of all, do I need the long divide? Why not?
You divide a couple is more than the
Right, denominator, the degree of the denominator is what's the degree of the denominator? 3, right? 3. You've got an x minus 3 and an x minus 2 squared. So 3. And then the degree of the numerator is obviously 2. So we're not going to long divide. So we got to think of all the possible denominators that we're going to need here. In this case, it's more than 2. I'm not saying it's all these, but I'm just saying we need to cover all our bases, right? We need to cover all our bases. So what's one possible denominator? X minus 3. And what will we have in the numerator? A degree 1 less than that. Okay, what's another one that we'll have? Okay, good. So x minus 2. Even though it's squared, we could have a fraction that just has a single x minus 2. Numerator. B. Okay? Because that's degree 1. A constant is degree 0. Alright, what else could we have? Okay, so x minus 2 squared is different than x minus 2. We need an x minus 2 squared. But it's still a multiple, or it's a power of x minus 2, which is still to the first degree. Therefore,
Yes.
but it's still, we're just taking this,
B squared.
no. It's just going to be, so it's still based on the fact that you have x minus 2, which is degree 1. Even though this is squared, this is not degree 2. Okay, this is degree 1. So it's degree 1. So we just need C. Okay, you're not going to use B again. Last of you are saying something to do with B. It's not going to be B again. You have a different constant for this.
So when it's squared in the original one, it makes it the bottom, the third degree, but when you put it down and break it out in decomposed form, it's first degree.
Yeah, you're focusing on the x minus 2. The fact that this right here is a linear, or degree 1. Okay, can you see how well you can do from there? Take it from there and see how you do. Okay, so what's the next step? Common denominator, and you're going to add these together. Okay, so if this was the start of the problem, and the problem was add these fractions together, what would your numerator look like once you did that? So what would your common denominator be, and then what would your resulting numerator be? See if you can do it, and you can compare with each other. Work together. Justin. Abdul Majid. Not here, right? Oh, you are. Sure. Talk to him. Ali. Alenzi. Ali, also not. Ahmed. Jeez. Abdul Rahman. No, that's not yours. El Mahmoud.
Or you can multiply it.
Yeah.
This is not the whole one.
Yeah.
Yeah.
I used to write down. I return to myself.
Yeah.
So when you see, is it right if I write down my name? It could be easier for you and me.
To do what now? Yeah, just write it. You want to go by nickname?
No, that's
Dom?
Yeah, that's
That'd be
fine.
wonderful. I would love that. Thank you.
Because
Okay, check it out. This is what you did. This is what you should have done. Did you get it? What do you need, right? So what do you need to multiply top and bottom by here to get the common denominator? What do you need to multiply top and bottom here to get our common denominator? X minus 2 squared. What do you need to multiply top and bottom here to get the common denominator? You need what? You need an x minus 3, but then you need another x minus 2. Do you see? And what do you need to multiply here, top and bottom, to get the common denominator? Just the x minus 3. So this is an exercise in adding fractions. It's just adding fractions. How do you add fractions? No calculus, right? This is not calculus. This is review. But you know, if you forgot, catch up. Alma Moon. Alma. This is Alma, right?
Yeah.
Because you need to consider all possibilities of what it could have came from. So when you add fractions, you need all the possible fractions that you could have added to get the one that we were given. So there could have been one that was over exponential squared. You see? And there could have been a separate one that was just an exponential. Better? Ali, Elsinore.
the whole thing together. The things that you want to get real. You get it? All the time, you know. No, you don't.
Then they will give me to square.
So
You only need 4, right? So 50%.
So you know that. Oh, I see. So just like sure, yeah. I can only go from expert.
Oh, just.
Yusuf. Yes. Okay. So our x squareds, I think we have an a plus b, right?
Yeah.
X squared, you're going to have an ax squared and a bx squared. So we're gathering our terms here, right? And then now x. So we're going to have, for x, we're going to have minus 4a minus 5b and plus c. That's going to be our x. And then constants. Plus 4a plus 6b minus 3c. How'd you do? That's the numerator. Does it make sense? Anybody have a question? So therefore, a plus b equals 1. Negative 4a minus 5b plus c equals 0. That's our x term. There's 0x, right? And then 4a plus 6b minus 3c equals 1. And then then we find a, b, and c. Anybody have it? So let's see. We can eliminate.
4A.
Yeah, but then, and then you could do. Well, that's not great because then you're left with a one that has B and C, and then one that has A and B. So instead, let's eliminate. If we eliminate C from these two, then what we get, we'll just have A and B, and then we'll have this one that just has A and B. So we can multiply this one times 3 and add. And that'll eliminate C, and then we'll get an equation of A and B, and we can take it with this one and get our A and B. So we multiply that by 3, and then we're going to add them together. So this would be negative 12a plus 4a. Negative 8a. It's on my pen. Okay, so I think that'll be negative 8a. And then this would be negative 15 and 6. Is that negative 9? And then we'll get the 0c that we wanted, and then equals 1. Did you catch it? So I took this whole thing times 3 and added it to this to get rid of c. And so negative 12a plus 4 is negative 8a. Negative 15b plus 6b is negative 9b. And then add, and that's just 3c, and negative 3c is 0, and 3 times 0 plus 1 is 1. Okay, so now I want to combine a plus b and this one, and that's going to be by going times 8. And if I times that first one by 8 and add to the blue one down there, it's going to make the a's go away. So 0a, 8b minus 9b. Negative b. 8 plus 1. B equals negative 9. So a equals, b equals negative 9. A equals 10. Is there an easy, somewhere easy to get C?
This is -5.
Negative 5? Anybody else get that? All right, we'll just go with it. Okay, so now we're ready to write we've got the decomposed fractions. We got, what, 10 over x minus 3 plus negative 9 over x minus 2 plus negative 5 over x minus 2 squared. And so the only new thing now here is, and that whole thing, what, dx. But we're doing the integral of that, right? Can I make it on the screen? Oops, jeez. Okay, so 10 ln of x minus 3 absolute value minus 9 ln of x minus 2, so that's just like the ones we had before. Okay, minus, okay, so now antiderivative, can you do it? Negative 5 over x minus 2 squared. Is it natural log? Can you do that? You should be able to do that. It's pretty easy antiderivative. So really we have negative 5 x minus 2 to the negative 2.
Negative 1 over 5. And 1 over 4.
I'm going to divide by 5. So this negative 5 is just going to come along for the ride, right? So we're going to have negative 5.
-5 times x minus 2 squared, or x minus 1 over x minus 2.
So x minus 2 to the
Negative 1.
negative 1. But when we take the derivative of that, what will we have? So I'm just pulling the negative 5 straight to there and just doing the antiderivative of x minus 2 squared.
-2.
You're going to do another negative, right? Because it's going to be negative this times to the negative 2. So that negative makes this positive. Do you see it? Did you catch it? Again, so if you're not kind of sure, you're like, oh, is there a negative? Is there a 1/5? What can you do?
Check.
Take the derivative, right? Take a stab at it. You don't have to get it perfect on this first attempt. You've done that before. Do something close and take the derivative of it and compare it to what you need. And then adjust your attempt. Okay? So let's just take the derivative. Let's make sure we got positive 5 times x minus 2 to the negative 1. So we're going to take negative 1 times 5, x minus 2 to the negative 2, and then there's really no chain rule to do here, right? And that's exactly what we get. Negative 5 over x minus 2 squared. Question?
Where did you get positive 5?
Okay, because we had a negative to start with, but then the power is negative 1. When you do the power rule, you're going to have negative 1 times x minus 2 to the minus 2. So I started with negative 5, but then with that antiderivative, I needed another negative. Other questions? Okay, so let's try. Yeah, please.
So basically, when you're basically making these equations for A, B, and C,
Yeah.
and then you're setting those equal to the coefficient of each power of x, like which is like right above.
I gathered all the terms of x squared, or all the coefficients of x squared. I gathered all the coefficients of x's from that, and all the constants.
Okay.
So I made it into a quadratic so that I can compare it to x squared plus 1.
Okay.
Does that answer it?
Yeah.
So then my coefficient of x squared has to be a plus b. We know that has to be 1 because we got 1 x squared up there. And then my coefficient of all the x's, which is this negative 4a minus 5b plus c, has to be 0 because it's going to be x squared plus 0x plus 1. and then I'm gathering all my constants, that has to be plus 1 because of what I have in the numerator up there. So that's right?
Yeah.
Other questions? Okay, so let me give you a couple for you to do and turn in. What did I do with those? Wait, actually, I'm gonna need to do. What did I do with my sheets? I had a whole big stack of them. Pull them out. Oh, they're there. All right, actually, I got to do one more example. Okay, so let's try this one here. Oh, we actually need to. So all the other examples I gave you, it started with where the denominator was actually factored into the different factors. Here it's not. So we got to start. You always start by, and maybe that should have been step 1.5 in my list, was get the denominator factored and then get the numerator unfactored, right? Because we know the numerator, we want the x squared term and the x and etc. But we want that denominator factored so we know the possible denominators in the decomposed form. So we're going to start by factoring. What does this equal? 10 over what factor? How does this factor? You pull an x out and you get x squared plus 4. Now we're ready to go. So, decompose form. First possible denominator. X. Okay. Next possible denominator. X squared plus 4. Any others? No. Numerator for the first one. A. Numerator for the second one. Okay, look. Now this is power 2. Okay? So this polynomial here is power 2. So we need one less up here, which would be bx. But that's not it.
Plus C.
Plus c. Okay, so when you have a power 2, your base polynomial in the denominator is power 2, then you need a linear factor in the numerator, which would be bx plus c. Okay, and now we're ready to go. So common denominator. So we're going to add these together. So we're going to have a times what? X squared plus 4 plus, what are we going to multiply top and bottom by here?
Bx plus C times
X. So it's going to be, bx plus c times x.
So Bx squared.
Over times x squared plus 4. We do the same thing as before. We're going to multiply out. So what are we going to have for our x squared term? We're going to have a plus
B.
b. So you're going to have bx squared, right there, and ax squared. So you're going to have a plus bx squared. And then what about for x?
C.
Just c, right? Just c times x. And then our constant? 4a. So a plus b equals what? Someone said 0. Agree with that? So we're asking, what's our coefficient of x squared in the numerator? 0. Okay. C equals. Oh, this is nice, right? Working out good. 4a equals 10. So a equals 5 halves, right? 10 over 4. And therefore b equals negative 5 over 2. And c is 0 already. We knew that. So we got it. We have 5 halves over x plus negative 5 halves x over x squared plus 4. And it's going to be the antiderivative of that, dx. That's easy. What's that? So this is our side work here. That was our setup, and here's what our integral equals. 5 halves over x is 5 halves. Natural log of x plus or minus 5 halves x over x squared plus 4. Can you do it? You should be able to do it. Should be able to do x over x squared plus 4. What technique or what are we going to apply to do that? You can't split it up. You can only split it up if it was something in the numerator with a single denominator. Okay, so you can't split it up. So look, we've got what? Got kind of the derivative here of this. So what is that? Undoing chain, and what we're going to have x squared plus 4 to the negative 1, so it'll be 1/2 ln of x squared plus 4. And we got the negative 5 halves I pulled out, and then all this right here is our 1/2 ln of x squared plus 4. Questions on this one? Okay, I'll write the problem down, and you can get started, and then I'll hand the sheets out. Last chance. Questions on this? Number 1. We'll do 2 of these. Number 1. Okay, number 2. You can go from here. Okay, those are the 2. You can work together.